So I'm curious here. Suppose I gave you a problem like number 12 and I asked you to solve it. How would you solve it? What would you do? Quadratic formula? Would anyone try and factor it? A couple of you? Okay, good on you. And if you try to factor it, you'd end up with, let's see, 2x minus 3 and 3x plus 2. So what kind of solutions would you end up with? Well, one of them would be x equals 3 halves. The other one would be x equals negative 2/3. So you'd end up with two real solutions. Now, you can actually look at these things and know whether or not they're going to factor if you do a little bit of work. And the little bit of work is kind of neat because it also tells you the nature of the solution. And we got two real solutions as opposed to some of the other problems where we got two complex solutions. But what describes that is a little piece of the quadratic formula. B squared minus 4ac over 2a. So this little piece right here, if this works out to be a number greater than 0, and by the way, this is called the discriminant. So discriminant is b squared minus 4ac. If b squared minus 4ac is greater than 0, then you get two real solutions. Two real solutions. If b squared minus 4ac is equal to 0, then you get one real solution. And last but not least, what's our remaining possibility? Less than 0. Now let's think about it. If this is less than 0, you're going to take the square root of a negative number. What happens when you take the square root of a negative number? What kind of number do you get? Yeah, complex or imaginary. Good. So get two complex solutions. So in the case of problem number 12, they really didn't ask you to solve it. I was just kind of curious to see what you would do. But if you take the time to calculate the discriminant, then we'll know a couple things. First of all, we'll know what kind of solutions we're going to get, two real, two complex, or one real. And secondly, if it turns out that the discriminant is a perfect square, then you know it'll actually factor. I'm not sure if it's worth your time or not. It's up to you. Depends on how good you are at factoring these things. But let's check it out. A, B, and C are 6, negative 5, and 6 again. So let's calculate b squared. Yeah, it'd be negative 6. Thank you. So b squared minus 4ac would look like this. Negative 5 squared minus 4 times 6 times negative 6. So that's going to be 25. A minus times a plus times a minus. What sign is going to go between these two? Plus. So 24 times 6 would be 144. So I get 169. So that tells me two things. The first thing it tells me is what answers the problem, is that I'm going to get two real solutions. I know that because this is greater than 0. But I get a bonus here. Because that's a nice perfect square, because 169 is one of those numbers on the left-hand side board, I know that this would actually factor if I took the time to factor it. Now, if you just want to use the quadratic formula and say, you know what, I hate factoring these things, that's fine. There's nothing wrong with that at all. But the point of this problem was to discern the nature of the solutions, and we have two real solutions here. Let's do two more examples like that. Let's take a look at problem number 16. 9x squared minus 12x equals negative 4. Before we decide the nature of these solutions, what do you think we have to do? Get them all on one side. Thank you. So I'll move the 4 to the other side. 9x squared minus 12x plus 4 equals 0. And why don't you play with that while I graph this and give this maybe a geometric interpretation. So okay, so A, B, and C should be 9, negative 12, and 4 respectively. So B squared minus 4AC is going to be negative 12 squared minus 4 times 9 times 4. So 144 minus 144, wait, let me get out my calculator. 0. So what's that telling me about the nature of my solutions here? One real solution. And depending on the circumstances, it's nice to know, what to expect. Let me give you kind of a different interpretation of what this means. And it's moving our way towards graphing these things in the next section. What if I was to look at y equals 9x squared minus 12x plus 4? And I asked you, find the x-intercepts. How do you find the x-intercept of a graph? Not just this graph, but any graph. Set y equal to 0. So if I set y equal to 0, 0 equals 9x squared minus 12x plus 4. Coincidentally enough, that's what this is, right? So in solving this equation, you're really finding the x-intercepts of this polynomial. Now, I was led to understand that there's only going to be one. Let's take a look at the corresponding graph. So take a look at the graph, and indeed, there's exactly one. You can figure out where that 1 is by factoring it. This happens to factor. We know that because 0 is a perfect square. This happens to factor as 3x minus 2 times 3x minus 2, or better yet, 3x minus 2 squared. So the only solution is going to be when this equals 0, or basically when x equals 2/3. Let's see that back on the graph. Now, a lot of this is extra, but it's building nice connections that I'd like to hint at. So there you go. There's your 2/3 and 0. The graph touches the x-axis exactly once. By the way, they have a term for this when a polynomial just kisses the x-axis like that. They use a Latin word. Latin words osculate. Osculate means to kiss, which is about as romantic as math gets. Yeah, sorry. So let's try one last one here, like that, and that'd be where is it? Problem number 18. So x times x minus 3 equals negative 10. X times x minus 3 equals negative 10. Let me get that up here now. That would help. Distribute the x, move the 10 to the other side. And then let's take a look at A, B, and C. 1, negative 3, and 10. So b squared minus 4ac, negative 3 squared minus 4 times 1 times 10. 9 minus 40 is negative 31. What's that tell us about the number of solutions to expect, or the nature of the solutions here. Two complex solutions. Two complex solutions. Nice. We could probably see that if we look at the graph. So let's change this. Let's put in a new graph. It'd be x squared minus 3x. And what was it, plus 10? Yeah, plus 10. So the question is, where does this graph cross the x-axis? And the answer is only in your imagination, right? There's no real solutions here. It doesn't touch the x-axis. So, nice. Okay, so that's it on discriminant. What we're going to move to is something a little bit different here. We're going to expand the types of polynomials we can solve. Yes, sir, Mark?
For the ones where you get like two real numbers,
Yeah.
you want us to explain if it's rational or irrational?
That's a great question. No, I'm not going to go that far. Just decide if they're real or not. They're going to be rational if that square root is something that'll simplify very nicely. A perfect square.
It says like two rational solutions, two irrational solutions.
I'm being nicer than the book. I'm not being less demanding. So, yeah, thanks. So, just to kind of clarify Mark's question here, he was asking, do we have to say what kind of real solutions? Because technically, you can tell if this number here, when you calculate the discriminant, if that's a perfect square, then you're going to get rational numbers, solutions. So, yeah, just two real solutions is all I'm looking for. Okay. So let's move on to solving equations that are quadratic in form. Equations that are quadratic in form. What on earth do I mean by that? Well, what I mean is they kind of look like they're quadratic equations, or can be made to look like quadratic equations. They aren't necessarily quadratic equations, but once we play with them a little bit, we can use the tricks that we've learned for solving quadratic equations to solve these types of equations. So let me put on a few examples of equations that are quadratic in form, and then we'll see if we can't figure out what they all have in common. So these will be the ones that we're going to do here. We'll start with problem number 24. X to the fourth minus 10x squared plus 9 equals 0. So this is not a quadratic equation. It's actually a fourth degree equation, but it's quadratic in form. Number 32, r to the 2/3 power plus 4/3, or excuse me, 4 times r to the 1/3 equals 5. That's quadratic in form. Problem number 40, t to the negative second plus t to the negative first minus 42 equals 0. And let's do one more. Problem number 28, t minus the square root of x, or excuse me, 2x minus the square root of x minus 1 equals 0. And let me help you out a little bit on this one. How could I rewrite the square root of x using exponents? X to the 1/2. And let me help you out a little bit more. Let me put a 1 there as the exponent of the leading coefficient. Okay. Now, there's something that's similar to all four of these equations. They all have the same kind of pattern to them. So the question is, well, what's that pattern? I don't get it. What's going on here? So why don't you think about it? See if you can't come up with a definition. Now, it doesn't depend on the variable, and it doesn't necessarily depend on having 0 on one side or not. Think about the exponents. See if you can't figure out a pattern in the exponents and help me finish this definition. An equation is quadratic in form if. So help me finish that off. I'm going to run and grab something. I'll be right back. But see if you can't come up with a definition for that. And look at the exponents. Did anyone figure it out? What does it mean to have an equation that's quadratic in form? Is there any pattern amongst the exponents, Mark?
So like a way that you can like factor or find a way to get it into quadratic form?
There is. There is something we're going to do to put it in quadratic form. Mitchell?
Basically saying that your exponent is what is that, 1/2 or 1/4?
You're right with the exponents. There is a pattern, and it's. Go ahead. What exactly is that pattern? What's the relationship between this exponent and that exponent?
Yeah, 1/2 of the exponent before.
Perfect. Perfect. So. Let me shift these. Okay, so the pattern is that the middle exponent is half of the leading exponent. So half of 4 is 2. Half of 2/3 is 1/3. Half of -2 is 1/2. Half of 1 is again 1/2. So that's the pattern. It's a pattern you're going to have to recognize. If the middle exponent is half of the leading exponent. Okay, so great. So now we got this wonderful definition. We can tell whether or not something is quadratic in form. Now, the way we're going to proceed on this is we're going to kind of trick our equation. We're going to make a little substitution to make it look like a quadratic equation and then solve it as a quadratic equation. So I've given you a handout, and let's discuss one of the problems on the handout. And really what I want you to do is just be able to observe this first problem kind of hands-free and try and understand this process at least a little bit. Now, can you see that this equation is quadratic in form? 2 is half of 4, so it's quadratic in form. Now, our trick here in solving this is we're going to make a little substitution. We're going to let u equal the middle variable term. Just that little piece, just the x squared. Nothing with the 15, nothing with the coefficient. It's just the x squared. So right here. Now what I'm going to do then is I can replace this by u. And let's see what happens if I square that relationship. If I have u equals x squared, what's going to happen when I square both sides? Well, I'll get u squared and equals x to the fourth. And that's exactly what I have here. So, do these two exponents add or multiply? They multiply. So basically you're doubling whatever this exponent is. So if you double this exponent and get this one, that means your equation's quadratic in form. And you can make this kind of substitution. That is, once you let u equal the middle variable term, then this u squared should be this term. Let's see what that substitution gives us. It gives me this equation, 3u squared plus minus 15u equals, or plus 12 equals 0. So, cool. Well, then what? Then this is just a regular quadratic equation. Hopefully you don't pull out the quadratic formula. You could, but you're better off factoring out the GCF. You factor out the GCF, and then you can factor a little bit more. What are the solutions in terms of u? What could u equal? 4 or 1. Now 3 doesn't affect the solution at all. Now an important question here for you. Were we trying to solve this equation for u? No, for x. So what we did is we kind of temporarily borrowed u. We used that to get past the difficult part. The difficult part was working with this fourth degree equation. We didn't want to factor and deal with that. That gets kind of ugly. But when we got past that, now we're done with u. So let's go back and say, well, u was equal to x squared. So now I got these two equations. But that's a little bit easier to deal with. How do you solve x squared equals 4? What would you do here? Would you take out the quadratic formula? Would you factor? What would you do? Square root property. Take plus or minus the square root, get plus or minus the square root of 2, or what's the other solution? So you get 4 solutions altogether. You get plus or minus root 2, plus or minus 2, and plus or minus 1. 4 solutions. It's no coincidence that that's a fourth degree equation and we got 4 solutions. That's not something you have to worry about until college algebra though. But there's an example of solving one that's quadratic in form. Sure, absolutely. All right. So the thing that we're going to do with our equations that are quadratic in form is that because sometimes factoring these things and working with these things is going to be difficult, we're going to trick our equation. We're going to trick it into thinking it's actually a quadratic equation. We can do that because it's quadratic in form. These exponents line up. This one is half this one, or this one is twice this one. Either way you want to look at it. Now, when this is the case, then you can let u equal this middle term. It's just a quick substitution. U equals that. Automatically, because this is quadratic in form, if I multiply this exponent by 2, as in I square both sides, then I get a term that I can replace this with. X to the fourth is u squared. So put together, this is u squared, and that's u. All right? And then the rest, you factor, and you factor and solve just like a regular quadratic equation. You just have one extra step when you're all done. You have to solve for x, not for u. Okay. Yeah, please. All right, good question. So we've got this times this equals 0. This equals 0 when u equals 1. This equals 0 when u equals 4. But 3 can't equal 0. So that 3 out in front doesn't really matter. It doesn't change the solution. We could add 3 or 3,000 out in front. It still doesn't give a solution. It doesn't change the solution. So, yeah, we ignore that part.
We have X out.
If it was an X, if we had like a 3X out front, then yeah, then that would change things. Then you could solve there. But if it's just a constant, if it's just a number, then it can't equal 0. All right, your choice. You want to? How about if we try and solve problem number? Which one was it? We had one of these that looked like that one. Problem number 24. So going back to problem number 24, it was x to the 4th minus 10x squared plus 9 equals 0. Lisa, how do I know it's quadratic in form? Yeah, this is half of this. So my substitution is going to be to the middle term. I'm going to let u equal x squared. Automatically, my u squared term is going to line up like it's supposed to. What equation do I get when I make those substitutions? Rachel? Perfect. U squared minus 10u plus 9 equals 0. Nice. Now this equation, you can solve it by completing the square, you can solve it by factoring, you can solve it by the quadratic formula. Yeah, not so easily by the square root property, but what would you pick? What's the easiest way to solve this one? Lauren? Factoring it. Yeah, factoring it. Good. So how would this factor? Anyone? U minus 9 times u plus 1. Or excuse me, u minus 1. Yeah. Yeah. If you can't, if you're looking at this and you're having a brain fart, you're like, oh God, and you're stressed out on the test, and you want to use a quadratic formula, absolutely. It'll work. And you know, I don't have any issues with using quadratic formula. I'd like you to factor because it's a lot faster. And you're going to get done with the test and have more time to look it over or just relax. But if you can't, nothing wrong with the quadratic formula. Now that gives me u equals 9 and u equals 1. But please don't finish here. There's a little bit more that we can do and should do because we're trying to solve for x, not for u. So what should I do at this point? Instead of u equals 9, x squared equals 9. X squared equals 1. So x is plus or minus the square root of 9. X is plus or minus the square root of 1. And I get a total of 4 solutions. Those 4 solutions are x equals 3, negative 3, 1, and negative 1. Okay, nice. Let's take another look at one of the problems that are already done for you before we move into problem number, say, 32. Before I do, are we okay with problem 24? Is there something, look, I know these are challenging. I've graded exams that have these problems on them for years, so, yeah? Well, we kind of put it in and take it out. What it does for us is it gets us past the uncomfortable part, which is the factoring. Now, sometimes people can factor some of these things and they can kind of get away without doing this step, and that's fine. But it's challenging, especially when you're looking at problems like, you know, number 46. I mean, not many people are going to say, oh, I know how this factors. It's challenging. So So what that step does for us is it kind of helps us get past the really tough part. But it's a temporary substitution. We do end up going back and substituting back in for x. So it just gets us past the tough part. Anything else on problem 24? Okay, so let's look at problem 46. And again, we're just looking at this one together. There is some stuff that I want to point out. It's understood, for instance, that there's a 1 here. So is this quadratic in form? Sure. Half of 1 is 1/2, so it's quadratic in form. What should I let u equal then? Rhonda? Good. Just the middle. Don't take the coefficients. Don't have to deal with the numbers at all. U is x to the 1/2. Now automatically, because this is quadratic in form, if you were to take the time and square both sides of this, you're going to get u squared equals x. So now you've got something here that, worst comes to worst, you can use a quadratic formula. You can factor this one. I'll be very candid with you. These problems are challenging enough. I'm probably not going to give you something that you have to do that AC grouping method to factor. It's going to be easier. So I'm not going to try and make this problem super, super hard. This one does factor. If you take the time to look at it, it factors like this. That gives me 2 solutions. What are my 2 solutions? So, well, you should be able to read off one of them. 1. And the other one is where 2u plus 1 equals 0, 2u equals -1, u equals -1/2. Whoops, should zoom out a little bit on that. There we go. Okay, so like I said, there's a couple things that I need to point out in this one. We're going to finish this up by figuring out where these things actually equal 0. So remember, u is taking the place of x to the 1/2. It's on the back side of your handout in case you're trying to follow along. Now there's a trick here in terms of solving. There's a couple ways you can think of this. You could think of this as being the square root of x equals 1. But I like thinking of it this way. X to the 1/2 equals 1. The trick to solving these things, and we're going to use it in the very next problem, is to raise both sides to the reciprocal power of the exponent. Now, leave a little room here for yourself, because I'm going to have to add a little bit to this later on. But right now, I'm going to raise both sides to the reciprocal power. So the question is, what's the reciprocal of 1/2? 2. All right, so raise both sides to the 2 power. Now when you square both sides, well, you get 2 times 1/2 is 1. And that's why this works so nice, is because when you multiply a number by its reciprocal, you're going to get 1. It's a quick way to solve. So one possibility is x equals 1. The other one is x equals 1/4. When you square 1/2, you're going to -1/2, you're going to get 1/4. Okay. Let's go back here with one little step. X to the 1/2 is also the square root of x. And just as kind of a reminder, when you square both sides of an equation to solve it, do you remember what we did back in chapter 9? After you squared both sides of an equation to solve your radical equations, what did you have to do? Anyone? Anyone at all? Oh, you had to check it. Good job. Thank you. So you had to check your answers, and when you check it, square root of 1 checks, Square root of 1/4 is not negative 1/2, so it doesn't check. All right, that's a little bit of an odd situation for us in these types of problems, but it does come up. Let's solve a couple more straightforward ones, and that would be starting with problem number 32. I think I said we do next, right? Yeah. All right, so let's look at 32. R to the 2/3 plus 4r to the 1/3 equals 5. So kind of like most of our work with quadratic equations, you're going to get 0 on one side. I'll move the 5 to the left-hand side. And now you look at that, and boy, those 1/3 and 2/3 exponents look really, really ugly. Really intimidating. Is there a way we can work around that? All right, good. We're going to make a U-substitution. Amanda, what should we let U equal? R to the 1/3. Yeah. R to the 1/3. Now automatically, if U equals R to the 1/3, because this is quadratic in form, then U squared is going to be R to the 2/3. That happens automatically. So let's rewrite our equation. Mindy, what would our equation look like with these substitutions, please? Instead of this, what could I write? Maybe some help? U squared plus 4U minus 5 equals 0. Lisa, does this factor? Probably. All right. Probably you can give it a shot. I'll start you out. U and a U. I'm so generous. One has to be positive, one has to be negative. All right, your ventriloquist. So positive 5 and minus 1. What are our two solutions then? Good. U equals negative 5 and U equals 1. Amila, are we all done? No. What else do we have to do? Yeah, please. They don't cancel out. We're just kind of working our way around them. We're just rewriting the problem temporarily. But actually, at this point, now that we've solved for U, we're going to realize, you know what? The original problem asked us to solve for something in R. So I'm going to go back and say, this is really R to the 1/3. So I didn't really lose my R's. I just kind of worked around using these fractional exponents. So R to the 1/3 equals 5, and R to the 1/3 equals 1. Now, to finish solving here, let's use the trick that I outlined just a minute ago. I want to raise both sides to the reciprocal power. What's the reciprocal of 1/3? 3. So basically it says cube both sides. Now if I cube both sides here, well, I get R. And negative 5 cubed, you can take it off your calculator, or you can trust me, either way. Negative 5 cubed is negative 125. So that's one of our solutions. What's the other solution? 1. Because 1 cubed is 1. Yes, sir. Well, yeah, you're going to raise both sides to the reciprocal of this exponent. So that exponent is 1/3. Its reciprocal is 3. So if you cube that, you end up with 3 times 1/3. That gives you R to the first power. which is just r. So you've solved it in one step. It's kind of nice.
So we don't use 2/3 at all?
Not really. The 2/3, we kind of bypassed that because we did this substitution. And that's what's nice about this substitution is that you don't have to try and factor something like that to the 2/3.
So when you have to flip the reciprocal, you always use the second exponent?
Yes, yeah. Your substitution, you're always using this middle term. Yeah. Now this only works when it's quadratic in form, but that gives you a lot of options. Let's solve a few more, finish out this section, and then get you on a break. Somehow I'm sensing that you want and need a break after this section. Let's see, which other ones did I promise you we would do? We do 20, let's do number 40. So t to the negative second plus t to the negative first minus 42 equals 0.
Don't you have to write those as figure? Just don't be like negative.
There's a lot of other ways we can do it, but let's just treat it like something that it is, and that is an equation that's quadratic in form. The middle exponent is half of the first one. So that suggests we can solve this with a U-substitution. What would I let U equal in this particular case? Not just -1. T to the negative first. And then if I square both sides, I get t to the negative second. So try and substitute it in, come up with the equation, factor and solve it. At least solve it for t. At least solve it for u. Maybe we'll solve it for t together, but at least try and solve it for u. I'm going to kind of walk around and help out. You can try and solve by raising both sides to reciprocal power. If you're trying to go further, finish solving this one, -1 is its own reciprocal. So it's kind of strange. There's I think two numbers that are their own reciprocals. 1 and -1 are both their own reciprocals.
Right, so far.
Yeah.
I was confused. Would it just be
Well, it's
equals
t.
negative
Well,
seven?
t to the -1 equals -7, and t to the -1 equals 6.
Okay.
Really? I was trying to think about that program. to see people get to is at least the factorization of the equation in U. So, okay. So, our equation should be U squared plus U minus 42 equals 0, which factors into U plus 7 times U minus 6 equals 0. And that gives me two solutions, U equals negative 7 and U equals 6. And then you look back and say, all right, well, U is really t to the negative first power. So here's where we're using t again. T to the negative first power equals negative 7, and t to the negative first power equals 6. Now, negative 1 is kind of an oddball in terms of how it works out, but negative 1 is its own reciprocal. So if I wanted to raise both sides to the reciprocal power, the reciprocal of negative 1 is negative 1. So I'm going to raise both sides to the negative first power. Now look at how fast this works out. It's really pretty nice. What's negative 1 times negative 1? 1. Negative 1 times negative 1 is 1. So that's t. And on the right-hand side, I get 6 to the negative first power, which is 1 over 6. Done. That's it. That's all there is to it. You can work this out a different way. I think Mindy noted earlier that, oh, wait a minute, you got something to a reciprocal power or a negative power. Sure, I could write it like this. I could write that as 1 over t. And I could multiply both sides of this by t. So t times 1 over t equals negative 7 times t. So I get 1 equals negative 7t. And then divide. Bless you. But, boy, I think it's a lot easier to just say, all right, let's just raise both sides to the reciprocal power. T to the negative 1 to the negative 1. The reciprocal there is going to be t to the 1 over negative 7, or negative 1/7. It's really nice and fast when you raise both sides to the reciprocal power. It works either way. You're free to do it either way.
Negative 7 to the reciprocal of the negative 1, that doesn't make it positive?
Correct. All it does is it puts that term in the denominator with a positive 1 as an exponent. And then in the next step, you move the negative out in front. Okay? So it's a good question. Yeah, you wouldn't be the first one to desire to do that. Anything else on problem number 40? Let's see. One more here. Problem number 28. I should do 28 since I promised 28. So 2x minus the square root of x minus 1 equals, isn't this? Is it number 30? Oh, okay. All right. As I said, number 30. All right. Now, one thing that you need to do for yourself to help out is rewrite the square root of x as x to the 1/2. And try and figure out what you're going to substitute. Rewrite this equation. I'll help you out with the factorization. Like I said, I will not give you one like this that requires you to play around with some really difficult factorization. Krista, what should I let u equal?
X 1/2.
Good. X to the 1/2, and u squared equals,
X to the first.
yeah, x to the first, or just x. So when I rewrite this equation, it looks like 2u squared minus u minus 1 equals 0. Now, in the interest of time, let me help you out with the factorization there. It's going to be a 2u and a u, 1 and a 1. That's going to be a plus and a minus. What are my solutions here? Mark, can you read at least one of them off? Good. U equals 1 and u equals negative 1/2. So let's go back now, and thanks, Mark. U to the 1/2 equals 1. Excuse me, x to the 1/2 equals 1, or x to the 1/2 equals negative 1/2. Nice. What would be the reciprocal power on this one? 2. So basically you're going to square both sides, right? So you're going to have x to the 1/2 squared equals negative 1/2 squared. So x is 1/4. And likewise over here, when I square both sides, I get x equal 1. All right, so this is the exact same kind of thing that we did in our handout, exact same problem. And the thing about this one is, right up here, when we had essentially the square root of x equals negative 1/2, that's what this equation is right here. What's the square root of 1/4? Is the square root of 1/4 negative 1/2? No, it's not. So that one doesn't check. Square root of 1 is 1. That checks. So if you plug this one in here, it checks. This one doesn't check. So there's really only one solution to this problem. Do you want one more or no? I know these are difficult, but it's your... Okay. Yeah, please.
So are these ones not necessarily plus or minus?
No, it's a great question. You'd use the plus or minus if let's see. You know, let me go back. You raised a good question. I don't think that it's a part of the problems in this book. It used to be in the other book that we used for this. But going back right here, raise both sides to the reciprocal power of the exponent. And I think I suggested to leave a little some extra room here. Use the plus or minus if the numerator of the exponent is even. So in this case we just did, the numerator of this fraction is 1. Is that an even number? No. So you don't have to use a plus or minus. You just square both sides and that's it. Earlier we had something to the 1/3 power. Well, 1 again in the numerator, that's odd. So we didn't need to use the plus or minus. Let's take a look at where we did use the plus or minus.
Problem 50 on this handout.
Problem 50 on this handout.
Thirds.
Well,
2/3 up at the top.
but you don't want to judge it by that. You want to judge it by the 1/3 here.
The middle term.
Right here. So when you're raising both sides to the reciprocal power, it's down right here. So it's the 1/3. So that's what you're basing it off of. So when we cube both sides here, we didn't need to use the plus or minus. But we did use the plus or minus for one of ours, and it was actually problem, well, if you take a look at problem number 36 that we did on the original handout. If you wanted to, let's take a look at this. X squared equals 4. You could think of the x squared as 2/1. And since 2 is even, that's where you need the plus or minus. So when you raise both sides to the reciprocal power is 1/2, 4 to the 1/2, but because that's even, that's where you need the plus or minus. So, Mindy, an example like what you're thinking about, or another example that might lead to using the plus or minus would be something if I had it to the 4/3. That would be an example that would eventually lead to using that plus or minus. Okay, there was one more that you guys wanted, so let's try problem number 26. Double check me on this. X to the 4th minus 15x squared minus 16 equals 0. Okay. This should factor pretty nice. Certainly much nicer than the previous one. I think you're going to get a couple imaginary solutions on this one. That's okay. And then just go back and say, all right, well, use x squared equals, u equals x squared, u squared equals u squared equals, or x squared equals 16, or x squared equals 1. Okay, so let's think here. We're going to let u equal x squared. U squared equals x to the 4th. So this equation becomes u squared minus 15u minus 16 equals 0. And that factors into u minus 16 times u plus 1. And that gives me two solutions of 16 and negative 1, just changing the sign there. But we're not interested in trying to solve for u. We're interested in trying to solve for x. So let's go back now and recall that u is x squared. X squared equals 16. X squared equals negative 1. There's a couple ways you can think of this. I mean, most of you would probably just think of the square root property, and that's fine. Take plus or minus the square root on both sides. Or, excuse me, plus or minus the square root on the right-hand side. I don't necessarily need it on both sides. You get plus or minus 4. It also works to think of taking and raising both sides to the reciprocal power. What's the reciprocal of 2? 1/2. Now, because this is even in the numerator, you would use plus or minus, but you're still going to end up with the square root of -1, plus or minus square root of -1. What's the square root of -1? I. So, again, we get 4 solutions. Now, I'm not sure you're going to see I as part of the solution. I think they might just be looking for real solutions, but it's a good reminder that square root of -1 is I. You know, if I was to write one like this, I'd probably write it so that you had 4 real solutions. I'm not sure that I'd be looking for them. And if I was looking for complex solutions, I'd warn you. All right? Yes?
I went directly from the x squared equals 16, x squared equals -1, directly down to the x equals plus 3.
Oh, that's fine. Yeah, you can do that in your head.
Do the...
You can jump from here to here. I mean, that's a step that I can envision people doing. I mean, keep in mind that sometimes I put in more detail than you would just so that I don't lose anybody.
Okay.
Yeah. But no, yeah, if you can bias this up, that's fine. I got no issues with that. For homework, let's see. Here we go. This is section 10.3. Oh, maybe. So demanding. 11 through 19, 23 through 33, and let's see, 39, 41, 47 through 51. So I'll tell you what, though. I'll give you the whole weekend to do it, all right? Yeah. I know, but I didn't get a huge success rate in terms of people completing their homework. So, all right, let's take a break.